Bismillahirrahmanirrahim. Assalamu alaikum. Um, can you hear me and can you see my screen?
Yes, sir.
We can hear you.
That's good. So we will be continuing our yesterday's um, content. We will be now. You have understanding of the supervised learning. So for the supervised learning, so you understand the classification problem and how to use that. So you have now an understanding of logistic regression, decision trees, random forests, support vector machines. So how evaluation metrics are important to evaluate the models. So again, we will be diving deep into the understanding the concept of unsupervised learning. And unsupervised learning, we will be starting from clustering K-means. So this is one of the topics in the unsupervised learning. So it means K-means, it means partitions data into K clusters. In order to give you a proper understanding of how it looks like and how is the understanding of putting data points into different clusters. This is one of the main topics within the K-mean clustering. It means in unsupervised learning, actually, the computer doesn't understand the context of the data, and also doesn't understand the labeling. So there is no label data given to the computer, to the machine. So computer will decide based on the patterns which are existing there. So the computer will decide so which pattern actually they will choose in how to divide data. Look at this. This is actually data points, yeah? So you just put data points. So this is x-axis and this is y-axis. Good. Now you have put different data points. What K-means actually does, the computer actually, computers look at the data points and thinks, okay, maybe this is, let's put all these data points into one cluster, put all these data points into another cluster, put all these data points into another cluster. So computer thinks, okay, if we divide the data into 3 clusters, so this is how it looks like. Actually, you didn't put any label to these data points. So the difference between the supervised learning and unsupervised is actually in label data. If you remember, we give the computer the understanding that, okay, if you have such a data set of customers, who will churn, who will not churn, yeah? But right now, we give a data set to the computer, which we actually just ask computer to find the clusters, actually, the patterns there. The computer thinks, okay, these 3 clusters would be much better. Now look at the colors, yeah, just in order to give you a proper understanding. Okay, this is the red color, this is the green color, and this is the blue color. But what happened? Blue, which is this center is here, this is called center of these clusters, yeah? So this data point become part of this blue. So you fine tune it again. What you're doing actually by bringing the data cluster centers closer to the category of data. If you bring green, green was here, yeah, was here. It was a bit far away. If you bring it more closer to this point, so this point automatically become green. It will be part of this. Why? Because K means clustering actually. It uses the distance between each data point, between these centers. They are called centroids. So if you bring this is called adjusting or hyper tuning of the model of KNN model. So you develop the model, and this is, you see this actually impacts your accuracy of the model. If this data point is actually green while it has been counted part of blue. Because why? Because the distance calculation between the centroids, or in a way that this point becomes part of blue. Now you hypertune that, you modify that properly, see, and you are still trying to adjust the centers, adjust these clusters, these centroids. You did this adjustment, then second time adjustment, then third time adjustment, then the final adjustment. Look at this. In each time adjustment, your centroids are moving. Data points are not moving, but centroids are moving. So these centroids are moving, and these are moving, and then now, finally, after k-means, it means after k into the k clusters, after the k-means, this is the cluster. So this center, changing the centroids and finding a proper centroid for these clusters is called iteration within the k-means modeling. So this is how finally this model brought the centroids within each cluster. And this is now the boundary of each cluster. And clusters are defined variable. So it means now computer understands that this is now the situation with your data. So whatever new data you are injecting, for example, a data here, for example, yeah, computer automatically thinks, oh, that's maybe blue, because it measures the distance between each centroid. So this distance between centroid to that data point will be measured. Look at this. If you put the data here, this distance will be measured, this distance will be measured, and then this distance will be measured automatically. The distance which is closer, that data point will be under that specific cluster. If you put data point here, automatically it will be under cluster 3 because it's closer to cluster 3 and far away from these two clusters. This is called clustering, and computer decides which cluster has. Then computer doesn't understand the context of the data, and neither you understand the context of the data, why these clusters are together. Yeah. For example, customer behavior. Yeah. You have lots of customers. These are data points, how they purchase everything, but you don't know how to divide them into categories. Yeah. Which categories? The purchase trend, the purchase habit. You don't know how to divide them into categories. But if you apply a k-means clustering model, then based on this method, computer will decide that these are the 4 or 5 categories that you can divide your customers based on the habit of purchase. This is how it helps humans, the computer, where there is no context behind that, and then you can get a context out with this model. This is why k means, it means that you have to define k clusters, how many clusters, for example, you want to have. So this is the point that you have to decide 3 clusters, 4 clusters, 5 clusters. Now coming to the another context of unsupervised learning. That's one of the contexts that that's called density-based clustering. So this density-based clustering is one of the things that currently one of the new topics within the machine learning, and you can learn it. Groups data points that are closely packed together, marking as outliers points that lie alone in low density regions. So what is the difference of this modeling with the k clustering? Actually, is the k cluster actually brings all data points into any of the clusters. So it brings each data point into any cluster. So whatever data points you're injecting, so one of these clusters will get that data, and it is actually calculating the distance between the data points. So this is the way how the k-means work actually. but 𝗘𝗍𝘃 is actually identifying a core border in noise points within that data point as well. And then things, maybe some data points or incomings become part of the cluster. But in 𝗘𝗍𝘃, it will not be part of a cluster. 𝗘𝗍𝘃 can identify that, okay, this data point is actually an outlier. This is the difference between these two methods. For the comings, it's a bit difficult to understand the outliers. In comings, clustering is very sensitive to outliers and all those things. If you didn't conduct checks properly, data pre-processing properly, if you didn't pre-process the data accurately, then comings clustering will become a disaster whenever you are applying that. So first step for the comings clustering is actually the very accurate understanding of the data pre-processing, outliers, and all these things. And then 𝗘𝗍𝘃 actually decides which data point is actually the core data point within the cluster, which is a border data point, and which is a noise data point. And what does it mean, a noise data point? Noise is actually type of how you can say it. It's type of an outlier actually. So whenever you are having several clusters together, and they are not far away from each other, then it will be very difficult to decide which is actually the proper data set, which is not the proper data set. The proper data point and which is not the proper data point. So this is how you will a very solid way of understanding the clustering method is this 𝗘𝗍𝘃. So I will bring you a visual which there you will be clearly understanding why it is how it's different from the clusters. In the coming clustering, see all these clusters are there. So this is how the clusters are there and how they work. Again, this computer really, what's going on? Okay. Look, these are the clusters, yeah? So coming works with these clusters. So this is automatic clusters. That density-based clustering is actually defines, look at this. You have different points for each point. So this is a main cluster, yeah? So this main cluster, the data points which happens within this cluster, that's called core points. The ones which are very far away, see, these are the far away data points. In 𝗂 clustering, there is no difference between this point and between this point, between this point and between this point. Everything is in one cluster. 𝗘𝗍𝘃 is actually defines that these are border points. It means they are far away from the center edge. It means there is a difference. And this is an outlier. See, it's totally one alone point somewhere else located. 𝗘𝗍𝘃 is a type of clustering, supervised, unsupervised clustering, which actually properly understands what's going on within each cluster. Within these data points, it gives you understanding of which data point is the core point, which data point is in the border side, and actually which data point is a noise point. Look at this, for example. Within this green clustering, if you take this one as a core data point, so this is actually either is going to be calculated as an outlier, which they are calling it noise, or not even as an outlier, but at least as a border point. So this is very good and very accurate whenever you're doing some assessments of which data points within each cluster is playing a key role. So that's very, very important to understand that and properly understand and digest what is going on within the within the clusters. These are some examples of clustering for unsupervised learning. And now we will be coming to the another topic here. That's called actually the I think one more. Yeah, that's the model evaluation within these clusters. So we previously learned how to evaluate the models. Yeah. Validate and hyperparameter tuning of the models. So previously we understand that. So currently we want to understand how the train validation and test splits work within the unsupervised learning. That's very important because you have to understand that, and you have to understand all those technicalities of what is a train set, what's a validation set, and what's a test set. So actually, train set is actually used to fit the model on it. So this is a set of data that we use to fit a model on it. It means to train a model on it. So this is how we, in our previous example, if you remember, we did such a fit of the models. Yeah. So we just used 30% of the data for the testing, and but the remaining it was for the training of the model. What is validation set? Validation is used to tune hyperparameters. Sometimes, if you develop a model, for example, like k-means, in supervised learning, it's not used. You're not using actually the validation set in supervised learning. So it's you can use it. That no one can say that you cannot use it. You can use it, but it's not that much having any impact on it. But in supervised learning, unsupervised learning, it's very important that you have to uh, um, have a separate set of data on which you have to fine tune the model. It means, okay, I developed a KNN model, and this is my model. Yeah, so this is my model. Okay, I thought that this model is, or just this model. I did this model, develop this model. This is for me at the beginning. It is actually the green, and this is the blue, and this is the red cluster. See, but at least I need to validate this model. Either this model is working properly or not, because in supervised learning, there is no need of validation because you have labeled data there already. How to validate your model? You're just predicting again on test set, and you have the result there. Yeah? You know the result there. So, for example, we had classification problem, logarithmic classification problem there in our data, and it was type of customer churned or not churned. Yeah, you have the result of it. If you want to validate your model, you're just running a test. And then within the test, you see how the model predicts and how is actually your data. In clustering, you don't have anything based on which that you should compare the data back. It means you don't have clusters, yeah, at the beginning. You just give the data to the computer. Computer did the clusters for you. Okay, and it gives me this cluster and say that this is blue. How I should know that this dot is not blue and this dot is actually green? This is how the point of validation comes in. Whenever you're doing any unsupervised learning, you have to always consider validation and keep a specific set of data for the validation to fine tune the model. It means then you will be doing iterations several times to come to this stage. You can do several iterations. Within several iterations, you will see that these centroids will be changing. The data points will be changing. And then you can fix the iterations in how you will stop. You will stop in a way that when we see that furthermore, these centroids are not moving any. Yeah, they will be moving in very, 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 very small amount. But this is it. That So this is the final place. So they are not moving any around. So whenever this movement of centroids or distances between the data points and centroids are closer to zero, it won't be never close to zero. But this difference is actually of movement is becoming closer to zero. Then you will decide, yeah, the model is now validated. Then you will do the testing. This is how testing in validation is very important, and um, it's used. Several people, several type of people, they are using different numbers for the validation. So this validation set is actually part of the training. So whenever you're training data and you say, okay, 80% of the data is for training, so put 20% for the validation, 60% for the training, and 20 other percent um, for the testing. One more thing which is called cross-validation. Cross-validation is actually splits data into multiple folds, training and testing on different folds to get a more stable estimate of performance. So what is actually cross-validation? Cross-validation is one of the another very important topics in this aspect. And we now understand that what is the validation set, but we can also discuss what is cross-validation. Um, Cross-validation is actually some people they are considering it as under the validation set, but I prefer that I will discuss it separately with you. This cross-validation is very important. It actually bringing the data into different folds. What does it mean? It actually divides itself the data into different clusters, and and those different clusters multiple folds, and those multiple folds will be having training and testing on those folds. So for each fold, the model will be doing some training and some testing, some training, some testing. Whenever all it's done, then the model will understand how is the performance of the model. What does it mean? For example, these are the clusters which have been finalized, and that's it. We decided if this model is actually performing well, yeah, performing well. Now, data points, whenever you're bringing new data points, for example, see this way. For these data points, we already understand these clusters, yeah? So these are the clusters. Whenever you're injecting a new data point here, it automatically calculates the distance and become part of one that cluster. But for the cross-validation of this, if you include cross-validation for the point, for the unseen data, what happens to the Cummings clustering? Whenever you're injecting a new data, it will not just calculate the distance of that data point to any centroids and decide which cluster it should be belong. No, it puts the data back to the raw side, to here, and put some new folds of data. So put some new clusters and then checking that which data, that data point, if you do the same thing again, so how that data point will behave, so under different folds. So this is an example of how cross-validation works. Cross-validation is computing heavy. It means it requires more computational resources whenever you're doing it. But still, it's one of the very good points if you want to have a very solid model and develop a very solid model. This is the difference between these these this method. But the model which appears from it, it will be a very solid model, and it will be very one of the most accurate models that you will be developing. That's called cross-validation, um, um, and this is how it will work. That the data will be divide it into folds. Now, one more thing which is called hyperparameter tuning. It's also type of okay, I will put this cross validation. So do we have the okay, so I will just put the definition of this cross validation here, that whenever you're using this later on, you will be understanding what's cross validation. Then we will be having hyperparameter tuning. And what is hyperparameter tuning? It's also type of um, developing the models. In what is the concept between hyperparameter tuning? You develop the model and you want to just fit the model properly, that it will should uh, find the best parameters that you set for the model. So that's called hyperparameter tuning. For example, for hyperparameter tuning, you will use two methods. One is grid search, tries all combinations of given hyperparameters. And another is random search, samples random combinations, more efficient for large search spaces. For example, who can tell me how you can hyperparameter tune a model in 𝗗𝗃? So whatever definition I give you right now, look at again. Grid search. It is tries all combinations of given hyperparameters. Random search samples random combinations, more efficient for large search spaces. So we have a 𝗗𝗃 problem. 𝗗𝗃's problem, sorry, not 𝗗𝗃. 𝗗𝗃's problem, clustering. For that, what do you think? What will be the hyperparameter tuning, the possibility of hyperparameter tuning for this model?
به نظر میاد یکیش enemy number of cluster باشه.
Perfect. Perfect. So number of clusters is one of the things that uh, is the parameter which you have to fine tune it. You should give them a number of clusters, this k. Okay, in our case, this k is 3, but who knows, maybe it is actually 2. Look at the data. All these data can be 1, and this is 2. So why 3 can have 2? Who knows, yeah? And who knows, it may be 4. Look at this. This is 1 cluster. These data are together. These data are together. These data. So 4 maybe. So who knows? So this putting different type of car here and searching for it. That's called hyperparameter tuning. And this is how it works. And you have to find that properly and understand which of them at the end give you the proper and appropriate result. So these searching for the car, either it's grid search or it's random search. What does it mean, grid search? In the grid, you're just giving different parameters. You're giving a lower value to the higher value. For example, you're saying, okay, find a cluster between 1 to 7. So this is actually grid search. It means you provided a grid to the model. Model will be searching for the number of K from one, trying two clusters, three clusters, seven clusters, and then at the end will combine all the results for you and say, okay, no, K equal to 3 is giving the highest accuracy. That's it. Or either you're just giving random search. It means if you have a very large data set. So for K means, so this random search is not applicable, but I'm just giving you a hypothetical example that if you give a grid, a random search, if you just allow computer to find the proper parameters, and and that's it. Then computer will do that searching randomly select the class, so randomly select any clustering. So this is how the difference between the grid search in random search is the difference there. So these are the hyperparameter tuning. They are calling it this hyperparameter tuning. So now going to the ensemble methods. So what is actually ensemble methods? Ensemble method is one of the difficult topics within the machine learning. So I will touch upon it, and I will give you this. This is a very large context, ensemble methods within the machine learning context, and we will be touching some topics like bugging and boosting. So what is bugging and boosting? So maybe you had other boost, gradient boosting, XGBoost. So these are the different types of models that you may have, but you actually don't know what are those ones are there. Yeah. So this is also a thing that you have to be familiar with whenever you are um, discussing the machine learning. So what is actually bugging and what's actually boosting? These are advanced machine learning methods in models, and bagging, actually it's called bootstrap aggregating. So this is the type of bag. It trains multiple models, for example decision trees, on bootstrap samples and aggregates their predictions, for example by averaging. So whenever you're using bagging or bootstrap aggregating, so what is that actually? It's actually using it, the computer trains different models. For example, we decided right now we will be using one Cummins, yeah, or we will be using one SVM, or we will be using this decision tree, yeah. So this decision tree. But in this bagging method, the computer will actually trains multiple models, and then it will aggregate the predictions. So the predictions will be aggregated to you, combined to you by averaging, for example, by averaging, but you can choose different ways as well. But it's still that's the concept behind backing. What is the concept behind boosting? Boosting is iteratively trains models, where each subsequent model focuses on the errors of the previous one. For example, order boost, gradient boosting in XGBoost. So what is boosting actually? It's a type of model, for example, XGBoost, if you're developing an XGBoost model, or if you're developing a gradient boosting model. What this model does actually? It trains itself. So you train the model. Okay. Now another model subsequently will be trained, and the aim of that subsequent model will be the focus will be in order to reduce the errors of the previous one. So the next model will be just concentrating on the errors of the previous one. So it will define the errors of the first model, then try to solve that error from the previous model, and then develop something new. So this is how, in a type of iteration, and it will be developing several models. This is called the difference between bagging and boosting, and these are one of the very advanced topics in machine learning, especially this mm, 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 the boosting models. Boosting models are used, and these are type of ensemble models. Uh, this is one of the categories under ensemble models. And for the boosting and for this bagging, you can also select whatever type of models you want. This is a method of machine learning, method of models development. Actually, they are not method, they are not models. For example, XGBoost is not a model. It is a way of modeling. It's a way of machine learning. Because you can, for example, in bagging system, in bagging method, you can just define, okay, I want to use decision tree. So decision tree, or for example, 𝗗𝗲𝘃𝗃𝗃 means um, um, and random forests and all these things. These are the individual models. What ensemble methods they are doing it actually, they're you're selecting one of them. For example, in one solution you want to select random forest, and another solution you want to select uh, um, mm, uh, decision tree. So you can have several models under these methods that you're seeing here. So it's a type of how the model will behave and how the model will be working. Now we'll be coming to another topic, which is called um, like the above. It's called stacking and blending. So this is also another type of way of doing the modeling. What is stacking? Stacking actually combines multiple models, the predictions using a meta model. The outputs of base learners are used as inputs to a second level classifier regressor. This is called stacking. It means you're developing several models for a problem. Then the outcome of that, all those models are becoming the input for another model. This is how this method is actually uh, working. Um, this is called stacking. And blending is actually a similar idea, but uses a holdout set to blend predictions. It means it's just blending the predictions. Uh, it is a type of stacking model. But for example, whenever the outputs of base learners are used for the inputs to the second level, so this is how each prediction of the previous model will be input to the final model. In the blending, so there will be one prediction. So it means it blends all the results into one and give it as a input to the final model. This is the difference between these two methods. Actually, they are not two methods; they are the same methods, but this is how it is. Now coming to the another topic, which is when we have very large and complex data types. So if we have those type of data types, so how to handle those complex data types? This is topics whenever you're doing modeling. For the small data sets, you understand, and you know how to do it. But for the larger data sets, it's a bit difficult to deal in. For the different mm, um, data types, it will be a bit difficult for you to understand how it is. One of the things that you have to understand, it's very, very important for you in the machine learning, that's called the time series data. Time series data is, for example, the data that you're having. Um, for example, you have sales data of a specific product since 1980s. Yeah, so it's not a one data set. Yeah, it's a huge data set, and you have it, and they are there actually. See, so it's a huge thing there. So this is called the time series data, and it has a huge data there because assuming, for example, since 1970s, you have something. Time series data involves, for example, observations over time. Approaches include, for example, feature extraction, lags, rolling means, and modeling techniques, for example, ARIMA, LSTM, and handling trends and seasonality. So within time series data, you have to understand the uh, just let me, if this code works for you, it will be giving you, let's generate this time series. Yeah, we generate some time series in values, random values in that set. Yeah, this is the date, this is the value, this is the value lag one, and this is the rolling mean. So these are the things that we have generated. So for example, you have stock value, yeah, for gold. Or for example, you have stock value for silver or something since 1970s. Yeah. So these are all the dates. Yeah. Or for example, if it's only data ranges only 2020, then you have stock values, for example, for Bitcoin or for any other coins for some things, and you have these values there. So this is how a time series data you have, and those are huge number of data sets, and you want to develop, for example, uh, uh, the modeling. So you have to mm, use proper and appropriate modeling, like for example, ARIMA and LSTMs, they are calling it, and um, you have to use the advanced time series specific machine learning models for it. This is for the time series data. You have to use those types of models. But if this is just a value and this is just uh, a date, but you have if large text data, so what to do with the large text data? It's called NLP basics, if, word embeddings, and all these things. So this is another topic within the machine learning, and you have to understand this topic. It's also one of the serious topics within machine learning. For text data, you have to use, first of all, you have to understand that computer doesn't understand the text. Yeah. So for that, what to do? First of all, you have to convert text into tokens. Then TIF ID for waiting words, and then uh, term frequency. It's called TIF ID. Word embeddings, word to vector, glow captures semantic meaning, and all these things. So what is actually text data? NLP basics. So the whole thing in social media right now, currently, you're putting excluding the picture, so the text, everything is going to is analyzing is analyzed by the machine. And machine, how it understands, it doesn't understand the language, but machine automatically embeds that, convert that text into a token. Token means a numerical understanding of that specific word. So this is how machine works. And what is NLP? Natural language uh, processing of the machine learning models. It is a type of libraries which analyze the text that you get. For example, right now you're typing to a chatbot. Yeah, chatbot brings you a response, and that response is actually based on NLP, based on a natural language, which the computer has the whole data of that specific language embedded into numbers. That's whenever you're changing it to to numbers, a specific alphabet to a number, that's called embedding. And then computer, what's computer doing actually? It's terms frequency. Terms frequency means computer sees which term frequently used in your sentence. So this is how the computer weighs, for example, bringing a context from a text. Computer doesn't understand the language, but computer mathematically uses different words that you used in that sentence, and using terms frequency. So which term frequently used, for example, sentence or in this paragraph. Then it gives a categorization for that specific paragraph. Or right now, for example, if you write just a comment in TikTok or maybe in Instagram, Facebook, somewhere, if you write a comment which has um, uh, not proper words, for example, so abusing something or just putting some not allowed words in those comments, automatically that comment will be blocked and you will receive a message that you are not allowed because it violates their terms of policy. How does it do? How machine actually? This is a simple NLP model. Automatically, that algorithm understands your comment, and then it has a terms frequency, and then it has a token which understands that which type of these phrases will be categorized under which those categories, not allowed and allowed. So this is how computer in NLP it understands. Word embeddings actually is type of uh, um, changing the the words into numbers. I want to try this thing. Okay, so if it runs, yeah. Look, these are built-in models. For example, I have three sentences. Machine learning is fascinating. Deep learning builds on machine learning, and natural language processing is a part of machine learning. Now, what I have done. So let's do TF-IDF vectorizer. So we use TF-IDF vectorizers. Builds deep fascinating is language learning machine natural off on part process. See how all these terms have been converted in how computer understands that. Look at this. This is the TF-IDF type. Then columns, we put that TF-IDF features names and all those things under each word. Now from this, look at this. Processing 0.4, yeah? 0.4 off, 0.4 part, 0.4 natural, 0.2 machine, language 0.4. So this is how frequently you used language. How much time you use language? Okay, one time. A learning, deep learning based on machine. Oh, it's just on this one sentence. Okay, so this is how machine understands the terms frequency. And one more thing, which machines. Uh, this is the original one. Yeah, this is the original. Fascinating here. It has 0.6 points here. Yeah. But after the fitting the TF-IDF vectorizer, so now it has 0. So there is no context of fascinating in these things. See, what is the context currently in this text is, let's find this, the context from this, which computer understands. Computer says that processing part of natural machine learning language is. So this is for computer the whole context of these three sentences. You got, so this is your original one. So in your original one. So this is how tokenization works and how vectors work and how the computer understands the context of a specific a word that you're giving it to the computer. So my just a very simple understanding that you have to understand whatever you are writing to the computer is just being converted into numbers and such numbers, and each number has a weighting there, and terms frequency and also the distance between them, the frequency. And also there are some words which are not used by computer as meaningful words. For example, on, off, is, that all these words are ignored by computer. Now computer is understanding. It's very intelligent now. that these are excess words. These are not actually the part of the context. So this is how computer sometimes ignores those ones. So this is the understanding of the whole thing. This was just a simple example. So we have time series data, how the computer understands that. So we have to use those ones. Now we have text data, and you saw how the computer understands those texts. Now, if you have, for example, image data, so how the computer will understand those images. So that's another thing that you have to also understand. It's called CNN, convolutional neural networks for the computer, which computer understands the image data. All the images are becoming pixels for the computer. So computer doesn't understand everything in very way that we are assuming. Its type of image preprocessing may include resizing in normalization. Convolutional neural networks learn spatial hierarchies of features directly from images. So it learns from the images, and then uh, it understands the hierarchies between the pixels. So this is how the image works uh, 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 within the understanding of the image in computer. And computer doesn't understand the image directly. It doesn't understand the nose. It doesn't understand the lips. It doesn't understand the anything else from whatever real world that we think. Computer doesn't understand that. Computer understands only pixels, and then it converts those pixels. It just analyzes each specific pixel. So you may hear sometimes, for example, 1024 by, for example, 768 or 780 pixels. Did you hear some of these things? So those are the type of things that computer understands and then analyze that. For example, we had a previous this data set in clustering. See this image. Computer doesn't understand that this is an animal or not animal. It analyzes all the pixels, all these pixels, small pixels. It analyzes all of them, and computer has a understanding of the uh, relevancy of the pigments of those pixels and their distances. In analyzing those pixels separately and the density and intensity of those pigments, and then the distances between each pixel. And based on that, then it thinks that is it an animal or is it not an animal? So this is called convolutional neural networks, and this is totally unsupervised learning type. Supervised learning is actually semi-supervised type of learning that you have to give some labels to the data labeling to the computer as well. Then computer based on that will understand the concept and will give you the what is going on there. So this is how computer understands the pixel from the pixel point of view, not from the whatever you're thinking that computer will understand in doing that. So that's totally different topic. There was an image. There was not an image actually. It was a research paper that I wanted to just show you, but still I think it's not working. But I will share that research paper to you, that how a computer actually understands the images and how it reads images. It's very interesting for the computers. Because sometimes whenever you are currently the social media is now in the position that whenever you are posting something, and if that picture is actually from somewhere which is copyrighted, yeah, it will identify that picture is actually copyrighted. So this capability is actually based on those all mathematical calculations. So the thing is that our understanding from machine learning is from human point of view, it's totally different what computer actually understands that. So computer is actually understands everything from a mathematical point of view, from array and matrix point of view, and from statistics point of view, not from what we are thinking it understands. Now coming to the one of the last topics in this model, which is our neural networks, and this is one of the interesting topics actually. So that how a neural network works. So within the neural networks, we have convolutional neural networks. So this is a type of neural network which is they are calling it CNN. So this is a very interesting topic within the image processing and neural networks, which is they are using it for computer vision. But still, that's not all the time the final one. Scenes or Calvinational networks. I'll just put the definition here for you, but then I will put scenes are actually convolutional layers to detect features and images. They are widely used in computer vision tasks like classification or object detection. So this is what I have mentioned above to you. This is a type of neural network. So deep learning and neural networks are a bit, this is how they are combined together. And because whenever you're analyzing the images, you cannot analyze the image without the understanding of the neural networks. What is actually neural network? Neural network is a topic, is a copy of how our brain understands the data. It gives, for example, it has nodes. It is a type of this one. Is a type of this decision tree. Is a type of decision tree. It has nodes. It has branches. So all of these things, assume that this is if it would be a type of neural network. For the decision tree, we have yes no. Yeah. In the neural network, we don't have any yes no. In the neural network, computer decides is it yes or is it no, based on what? Based on all the specifications that you're providing at the beginning. All these lines here, we have only one solid number for it, yeah, in decision tree. Either it is 0 or it's 1. This is 0, it's 1. In neural networks, all these has values, starting from 0 to 1, something, yeah? So 0.9, 0.2, 0.2. In all these values, and it has maybe not only 2 nodes, it can be having several nodes. And each of them are separated by a layer. It's called layer. Such type of layer, this type of layer. See, this type of layer. So this is how a neural network works. So then it has been separated by layers this way. All of these are separated by layers in each layers, and then each layer analyzed separately. And whenever the calculation happen here, for example, it says, okay, this is a picture of animal. It goes back. This calculation goes back to all these lines back to in the neural network. It means this is a back propagating and front propagating functions, which neural network has, and neural network understands that way. This is, I think, the most important point that you will understand from what is the how the neural network works like. And This is the understanding of how computer understands the neural network. Neural network is not used for the images. It can be used for different types of questions, and maybe you heard about deep learning. So there is something deep learning. Yeah. So that deep learning is actually part of the of the uh, neural networks. It means the computer actually dives deeper and deeper into the problems, into the different layers, and then categorize something into something. Says, okay, that's that part of it. Um, Computer is not working properly. I just wanted to show you neural network. Uh, See if it runs. Yeah, it runs. So this is a type of neural network. It's called TensorFlow neural network. So look at this. These are your features. Yeah, you have features and you have neurons. All these things are neurons. And this is the output layer. So how many hidden layers you have? Within a neural network, these are the things that you're having. What is epoch? Epoch is at the time which it runs the iteration. Learning rate is one of the hyperparameter tuning points within the neural networks. Activation, which type of activation function you will be using. You will be learning these by yourself. We will not diving deep into this because it's not part of advanced learning. But just assume that we are using sigmoid function, for example, right now for this, or maybe if just tangent function, or linear, just linear function. So assume that we are using sigmoid. Regularization, I think what is L1, L2, so assume that that's none. Regularization rate, how much will be regulated? A problem is classification and regression. So you want to have a classification, you want to have a regression. So assume that you want to have a classification. These are the features that you provide to the network. See, and these features, and these are the 4 neurons that you are having, and this is the data. These are your data points. Now, computer decided, okay, that all these data points, these are blue, and all these others are actually the orange one. This solution, this problem, this classification problem can only be handled by a neural network, not by anything else, even not by Kainan cluster, Kainan means. Why? Because within Kainan means, if you select this one cluster, this another cluster will be selecting, and it will be involving this cluster within it. To me, you saw that, you understand that point. Or otherwise, all these things will be clustered in different points of view. So this is how the this is the learning rate, yeah, 0. So the highest the learning rate, the lowest the learning rate. So this is how it will learn. You will continue training the TensorFlow or training a neural network that this line, which is this learning rate and test loss, training loss, actually become the same. So this is test loss and training loss. It means this is the highest possibility that these two are different categories. You got, for example, you can add more neurons here. You can just get some neurons deducted from it. So you can have several hidden layers, for example. Right now we have 3 of them, yeah? So in one layer you can have 4 neurons, in another layer you can have 3 neurons, for example. Assume this is another classification problem, yeah? If you just start in running, so this is the learning rate. So how it trains itself. So this is important. For example, just think of tangent and put the learning rate to 0.1. Then let it be the classification problem. So it then defines for you the classification problem. So you have 2 classes and you want to define 2 classes. See, either this one is 2 class, but that will not be right, yeah? Or this one, that will be not right. Now, these neurons, what they're doing? This neuron, look at this neuron. This neuron is changing. So, do you see the changes here in this neuron? This neuron is actually dividing. This way is dividing the data. This neuron is dividing the data that way. This neuron is actually dividing the data in this way. This neuron is dividing the data in this way. Now, they are actually now dividing the data in curved sites. See these curved sites? These are the curved sites, yeah? This is another type of division of the data. This is four type division of the data. So this is how they are fine-tuning themselves, these neurons, in another layer. Now, this is how the negative neuron, and this is how the positive neuron. So they are training themselves, and they are bringing the two layers for you. This is the training function, loss function. It is now in a way that 0.04, it's not changing. When it's not changing, you can stop the training of the neural network. You stop the training of neural network, and that's it. This is your final neural network. So whenever points you're putting, it will decide which sector. Look, even these small dots in the borders have been decided properly. All of them, look at this. All of these lines, they have a weighting. See, there is a weighting. Weight is 0.88. This is it has a weighting of minus. It means it's not relevant totally. It has a minus 0.004. So it has a 0.86. So it means this cluster, this weight for this cluster is the highest, for example, whenever going from this neuron to this site. So what what does it mean, this point for these weightings? So all of these data are inserted to this neuron. See how the neurons are providing the data. This providing the data for the orange cluster. This provide the data for the blue cluster. This is for the orange cluster, and this for the blue cluster. And also it provides the biases. So it means this neuron is actually biased by orange cluster. Yeah, see? And it's actually biased by the orange cluster. These are some data points. These are some data points which are blue, but they are under orange. See? This is how a neural network trains, and it give you different. You can add noise for your data. And for example, change the data totally that way, this way. You can have batch sizes, for example, different batch sizes you can have. These are the parameters tuning of the data. And then you can just run the neural network again, and then neural network, you can have, for example, here, 4 outcomes neural network will define for you and find for you. So which 4 categories, classifications, and how to find that for you. And see, this is changing. The computer understands how to read that. So this is the highest. Look at this. It just adjusts itself. This is how neural network works in computers. It's type of like of a brain. These dots, whenever this comes to this point, it goes back to this side, then it comes back to this side. This is how a neural network is very intelligent in working with all these things. Now it will again find you some 2 or 4 classes, but I added noises here. See these 13 noises here. These are noises. I add noises to the blue side, these orange ones, and blue dots to these orange ones. These are noises. See, this is why it not gets fit. See, this losses this much and training losses this much. It's not getting fit to each other. Whenever these are fitting to each other, it means that will be the final classes. And then you have to wait for the computer. This is one type of classifications. This is another point of classifications. It just brings data to different clusters totally, and defines the boundary between 2 clusters. And this is even the classification for the spirals. See, it's different types of, even if the data is like this, it understands and classifies. However, this is uh, this is how neural networks work. This is the advanced topic of machine learning. Uh, And for the image, it also gets the RGB. So the RGB is also very much important whenever you are analyzing the images for the computers. So we have uh, other topics within machine learning, but we will not be discussing those topics, for example, model deployment and other things. We will ignore those ones. And we will be just conducting a very simple, I think, course practice right now. I think you will like it. Um, it's about an agricultural project. It's one of the things that um, we will be doing that in a practical work right now to understand the modeling. These advanced topics are just for your information, so you will have that. So I think let's have a 5 minutes break, and I will be just preparing the data and see how to use the data for this practical work. If you have any data set, please let me know. You can work on that data set directly. If you have any data set and you want to that we can work directly, you can do that. Can you hear me? I don't hear any of you. So I hope that's not the same problem happened previous time.
صد میشنویم صدایت. اینجا دیتا ما دارم گوگل درایو بس ما لینک شیر
شیر کنیم باز چی کنیم لینک رو؟ خیلی.
چی خمسات؟
خب برای من شیر کنیم دیتا ستتانه که خیلی میال کار عملی رو شروع کنیم اگر
باشه
میخوایم.
باشه همیل شیر
اگر من یک دیتا ست دیگه دارم it's not good. دیتا ستتان راجع به چی است؟
یکی تایتانیک بود دیتا ست تایتانیک و دیگه یک اپل کوالیتی پردیکشن یک پروژکت دیگه بود دیتا ست دو هم هسته فعلا یک دقیقه باش ماشین اما تایتانیک استاد خوب هسته اگر
نه تایتانیک دیتا ست بسیار قدیمی است.
خواستی استاد چت باکس شیر کنیم سه
چی رو شیر میکنی؟
لینک گوگل درایو استاد
شیر کن. کدام کسی مسیج موندن گپ نمیزنن. Have about quality education. I have about quality education if you need sir. من یک دیتا ست کار دارم که چی باشه؟ پلان گروت نو پلان گروت دیتا ست کار داریم که بتونیم یک چیزی پردیکت کنیم از اونی ولی یک مشکل باشه که از اون یک راه حل برش پیدا کنیم عملی. از او خاطر من گفتم اپل کوالیتی باشه کلی دانلود شد. Yeah, Apple quality, just save it. Mhm.
وسط لینک کاغل هم اپلود کردم، اگر از اینجا شیر دانلود نمیشه میتونی از کاغل بگیری.
کجا میشم شریک کردیم؟ دوست خب کاغل رو شریک کردیم. علی سیرتون یه دوست شریک کرد که ابو شما رو باز کنید که چی هستی؟ اول کاغل رو باز کنید ببینیم که چی هست. خب این راجع به اپل هست، راجع به کوالیتی اپل. اوکی
بله.
گود. یه دست very دیتا ست خوب است. باش هر دو دیتا ست کار میکنیم. So yeah, we will be then. Yeah, that's very good. So یک شده اینجا کار میکنیم، در خود اپل یکی اینجا کار میکنیم. So one of the data sets which today we will be working with, we will be starting with today. The whole session will be about the agriculture. So I have a data set. It's called soil measures, and I want to find it. Or where to find it? Oh, just want to upload it. Let's forget about finding it. Otherwise, it will take a long time. We will be inserting this data set and we will be uh, analyzing this data set. Okay, just let's assume that this is this data. I hope other things are here. Import handles PD, import as NP, and no, not TensorFlow things, and all those things, not those ones. But we need promise learn. Mm, we need logistic regression, and we need metrics. All these things. Now let's enter the data. PD dot read page3, and this is copy path and paste it here. Okay. Then just assume what is this data is about. Oh, this data is about an agriculture soil data set. It gives us the different measures here. What are these measures? This is the nitrogen content ratio in the soil. P is phosphorus content ratio in the soil. K is potassium content ratio in the soil. pH is value of the soil, pH value of the soil. And crop is the relevant categorical crop that we want to have in this agriculture land. You know, one of the main problems within the agriculture sector is that actually the farmers, they don't know what to what should be the harvesting plan. So there is no harvesting plan. Actually, a farmer, based on its experience and his experience or experience of his dad or experience of his other family members, they are just deciding, okay, they will the harvesting. This will be the harvesting season and how it will be. Actually, this decision is not data-driven decision. Countries who are really much relying on agriculture sector, one of the main problems for those countries are actually that they are not, or even the farmers, or even the people, the governments, everyone is not paying attention to the data side of that. With the global warming and with the situation which happens in the environment, the seasons are getting changed. So you will not rely on the data that you had 40, 50 years ago that your dad conveyed to you, for example, to a farmer, that, okay, this land will be suitable all the time for the rice, for example, or all the time for that, for something else, for any other type of crops, for coffee, different types of crops. So this is how, and this is a huge data set. Look at around 2,200 data set number is there. So this is how you're thinking about agriculture. And one of the failures of this agriculture is actually this is how the farmers are not making a decision based on a data-driven decision. So the machine learning is not a tool which should be used by some elite people. Machine learning, modeling, advanced data analytics, all these AI, actually currently in the Western world, it's something that the specific number of people they are having access to it. But it should be vice versa. It should be a tool in the hand of a farmer. It should be a tool in the hand of all those deprived communities. Based on using of these tools, they can make accurate data-driven decisions, and enhance their economies. While we understand that they don't have that amount of sufficient level of literacy or digital literacy, but at least if one guy in a village or two guys in a village, they are going to be keen to do this for their own village. So I think it will be a huge another revolution, technological revolution within all those villages and deprived communities. This is the primary objective of this machine learning problem that we have to maximize the yield of their crops. So taking into account different factors. The factors which we can do that take into account that which crop should be harvested. It's very easy. If you have conduct any soil tests, these soil tests are very cheap and can be conducted very easily. And if it has been done, so and then the result of the test is there, then you can decide which crop is the optimal choice for that specific field of land. In this data set, we will be building a multi-class classification model to predict the type of the crop and identify the single most important feature for predictive performance. So can you tell me, okay, so this is now the div that you have, the data. Let me do something else. Data, all the time you have to do data.info, then you have to do data.describe as well. So these are the things you can do that. So can you tell me which of these solutions we should choose, models we should choose? So first of all, tell me, is this a supervised learning or unsupervised learning?
It's supervised.
Okay, okay, if you can elaborate a bit more.
Because you have given the features like nitrogen, potassium, phosphorus, and pH. So that you have categorized the features. Yeah.
No, we didn't categorize the features. What the model, the type of model will be decided based on the what we are predicting. We are predicting crops. Yeah, which crop will be feasible.
Yeah.
So that crop is categorical. Yeah, crop is categorical value, and we have actually data dot crop dot value count. It will be this much type of different multi-categorical crops that we are having, and these are the different value counts for those crops. So this is how we are predicting any crop, and those are categorical. So a multi-level or type of we are calling it multi-class classification model. We call it multi-class classification. So that's not only two, which binary one, but you can do it multi-class. So if it would be just binary one, for example, two class, either rice or just cotton, for example, yeah, which model type you will be selecting? Which specific model you will be selecting? Who can tell me?
So logistic regression.
Logistic regression would be selected for the binary classification if it would be two of them. But right now we have multi-class. Yeah. For the multi-class, either we can use random forest or we can use decision trees. Yeah, decision tree classifiers, because this is a supervised learning, and within supervised learning, it is a classification problem. Yeah, within supervised learning, we have classification. Look at this supervised learning classification problem. Either it's logistic regression, decision tree, or random forest. So logistic regression is, we can use that, but it predicts actually using the logistic function, but it's not fitting for this problem because it has lots of categories there. If it has two category binary decision making, so logistic regression would be a best option for it. But you can use multiple logistic regression, but instead of that, decision trees would be the suitable point for that. This is the model that you have to select for a problem before going deep into the problem. So this is the start of the selection of a model in a problem there. So now, whenever you say, okay, this is the model that I want to use, now you have to bring the specific libraries from scikit-learn for that specific model. All the time, look at this model selection. See, scikit-learn.model selection, import trend test split and cross validation score. So both of them you can bring. From scikit-learn.tree, you should import decision tree classifier, and from scikit-learn preprocessing, you can import label encoding. So these are the libraries that we need to bring. And why this is important? First of all, do you remember that we have to encode the categorical target variable? Do you remember what we have learned? And we have now categories, yeah, these crop categories. Now we want to do what? We want to predict which crop is suitable based on these classes, which is suitable, yeah. But these crops, these are not numbers. These are categories, yeah. These are labels. So before going to the model, in order to have a very appropriate and proper understanding of that model, you have to do the label encoder. And why that's important? Because if you don't have the label encoder there, then that will be, these crops will be, the computer will not be understanding these meanings of these categories. So whenever you are having categorical and you want to predict categorical values, text which are text, you have to do label encoding. So I use label encoding. I use label encoder, which I imported from scikit-learn. And what I have encoded, the crop. This crop has been encoded into I encoded to the crop encoded. So I created new data set, a new data. It's called data crop encoded. Now look at the data. Look at the data. See, this is how the encoding happens. Computer now understands these numbers, while rice, computer doesn't understand. Coffee, computer doesn't understand. Now computer automatically encoded this label. Computer said, okay, rice is, for me, number 20, it means rice. For computer, this number, because computer understands numbers, yeah? It doesn't understand the words, the alphabets. This is called label encoder. So first of all, you have to encode these coffees, for example, number 5 for computer. See, this is how computer understands. This is why encoding is important. And I hope now you got the context of how encoding is. Now, after encoding, what to do? Encoding is done. We did encoding. Now, what to do?
Split the data.
Yeah, if I think you're the only student we are having in this course. I thank you. Yeah, we have to split the data. Now we have to give the computer an understanding that what is actually the training set and what is the target. Now we give to the computer the understanding that this nitrogen, potassium, phosphorus, these are the inputs for you, and crop encoded this column. This is the target for you. It means this is what you have learned, the patterns, and this is what you have to predict. So this is called, we are splitting the data. So you have to split the features and you have to split the target, define the target. After the features, which we have split it and defined it, we have to initialize the classifier. So the classifier, which you know that we decided that we will be using decision tree classifier. Now you have to initialize that classifier. Classifier is called decision tree classifier, which we already imported from here. And we just choose a random state of 42 that whenever it runs, it should give the same responses. Otherwise, it will not give the same responses, and it will just be different things. Now, one more thing that we have to use, that is that we have to initiate what? We have to initiate a blank dictionary of feature scores. Yeah. And then what to do? We have to find for each feature and X columns, for each feature score in X column. What will be the scores? Scores will be the cross-validation score. Cross-validation score of what? This classifier. We will be giving to this classifier, which is decision tree classifier, the X features, and then the target, and then that target and features will be classified by this decision tree. Then scoring will be the accuracy of that specific cross-validation score. That will be the scores. Then the feature scores will be from the feature. Then it will be the average of all the scores which each feature gets under this decision tree classifier. This is the average of nitrogen, the phosphorus, the potassium, and the pH of the soil. So these are the average of scores which this decision classifier brought from the whole data set that we got. These are the accuracy, the feature scores. What these scores actually means, the scores for each feature is based on their ability to predict the crop type using a decision tree classifier as follows. For example, nitrogen is 0.16, phosphorus is 0.19, potassium is 0.29, and pH of the soil is 0.13. So the feature potassium content has the highest predictive performance with a score of approximately 0.29. Now, you got what we have done here. What we have done here in the cross-validation score here. In the cross-validation score, these are the features, yeah? X are the features. These are the features. And this is the crop encoded. What we have done here in the cross-validation, we find that which feature, this is called the second thing that another step that we have to take, that was the feature engineering, yeah? If you remember, in the modeling. This is part of feature engineering. So we have different features. Now, which feature is very much important in this model? With this simple line of code, we defined that actually potassium is having the highest score here. So potassium is the most impactful, one of the most impactful features in this data set. So if you want to predict the crop type, the crop type of crop, what to harvest, role of nitrogen from test soil is 16%. Role of phosphorus is 18%. Role of pH of the soil is 13%. But role of potassium is actually 29%. So it means this 29, 0.288 or 0.29. So this is the score, average score of potassium, which plays a key role whenever you're deciding which crop to invest. So this is called feature engineering. Instead of training a whole model on all of these things, what we have done a very small step here. That's called feature engineering. We identified actually potassium is the most important. Instead of all other things, let's just use potassium, and best predictive feature for this model is actually potassium. Now, based on potassium, and then based on other based on crop, which we have right now here, yeah. So we encoded the crop. What we can do next, we can just simply predict a very simple model, developing a simple model to predict for each crop if we have the amount of potassium. We can see under which crop which amount of potassium is there, yeah. Then for each crop, for example, just it doesn't even need a model actually. It is actually data, the crop, data dot group by crop, and take the cat, yeah. Size, take the cat and take its mean. See what's happening. So the potassium average for apple is 199, yeah, for banana, for so now just assume there is no model even needed for this, yeah, further modeling. We have already used the classifier model here. We understand now potassium is the highest. Now, based on potassium, okay, I have a soil test, and it has lots of other features, and the potassium is, for example, 55. Just assume it's 55, yeah. So look at this. 50 is suitable. The average potassium for banana, to crop banana, is 50, yeah, for example. And muskmelon is 50.08, for example, yeah. 50.05 is papaya, for example. So papaya, muskmelon, and banana, these are all these are actually the same things, you know, from our country's perspective, because we don't have these crops in our countries, but Caribbeans, they have it and they understand it very well. So this is how for them. 50.22 is actually watermelon. Yeah. So it's more than 50, but less than, for example, 60 or any other things. So if it's a bit more than 50, so you will proceed with what? With just directly using the watermelon, for example. If so, from this categorization, even you can decide which type of soil you have, and which type. Look at grapes in our country. So the soil is very rich soil with potassium. So it would be 200 even. So that's how. Look at the cotton. It's the lowest potassium needed for that soil. Look at the coffee, for example. We don't have coffee, but it's still. So watermelon, yeah. So this is one of the things that we have in our western side of the country. So this is how we just defined from in this modeling of activity. We just defined which feature is the highest important. We found the potassium is the highest important, and this is the important feature for this model. Just ignore other features. Now you can decide based on potassium which type of crop you can just harvest. This is one of the machine learning problems you can tackle and how you can approach to that. Don't go just think about it that okay, we will uh, go deeper to that, and then uh, understanding different types actually make it difficult, actually, for example. So just please don't do that. Okay, now let's okay, what is this? This is download dataset. You give me the dataset already. Yeah, you gave me the dataset. So the dataset is already there. Okay, good. So where you want to do it? Should we do it in Kaggle, or we should just bring the data set here? Danish? Okay, there is no one, but I will continue upload this data set, the new data set which they send me. Now let's start with this data set and see what type of data that we are having right now. Okay, so we will be having data 2. It will be vd.read csv, and it will be the Apple quality data set. Okay, copy path, and that will be the Apple quality data set, and let's analyze that. Okay, now going to the next step, let's explore the data 2 and see what's there. These are the different aspects of a data set, and this is the quality of the Apple. So I think it's the ID classifier. This is the size of the apple. This is the weight, sweetness, crunchiness, juiciness, and ripeness of the apple, and acidity. And then you have to decide which quality of that is that apple is actually which quality. So before doing anything there, quality is actually the type of the target that we have to. It means that we examined an apple in a lab, and then which category we should put it. We should put it in good, bad, which category. So this is a classification problem. So we have to define the class of that specific apple that we have to put there. First of all, we have to do what? So we have to drop some columns, for example. Let's drop the Apple ID column. So this is not playing a key role here. See, this ID is not playing a key role. And actually, if not playing a key role, it will just disturb the model. So data 2 will be we want to drop a feature actually, because that's not an important feature. It will be data 2 dot drop what actually? Drop columns equal to a underscore ID. So just drop that. Now look at data 2. This data 2 is now, what happened? AID not found. That's good, we dropped it. Okay. Sorry. You should put it here. Here we already dropped the column, yeah? So whenever I run it again, so it says that there is no AID, so because it was dropped. So this is now that we dropped the AID there. So that's not an important column there that we have to drop it. One more thing, that acidity, I think. What's this acidity here? What's this? This is acidity. Yeah? Oh, okay. Just before going to that, let's see the data.info. What is the info? Look at this. Oh, data 2. Data 2 is .info. So this is the sizes, the float. Acidity. Acidity is the object here, while it should be, these are the numbers. So we should change that acidity into the number. So how to change the acidity? So we will be saying that data 2 of 𝗤2 acidity column will be equal to the PD. This is a new functionality that you can do. Look at this. Let's just run it. And if you run the 𝗤2.info, it is now numerical. That's brilliant. One more thing, we have to find the missing values. So how to find the missing values? Missing values will be equal 𝗤2 is null dot sum. Now print the missing value, and almost all of them, they have one missing value. And what we can do, we can just drop those numbers. It's just one number. Just drop it. 𝗤2 will be 𝗤2 drop now. It means miss all those, drop all those null values. So null values have been dropped. That's good. Oh, we are 2:30. We have done the some data cleaning process. Now, what will be the process? The next process, we are doing some classification problem. For the classification problem, now we have this quality of let's see, 𝗤2. This is the quality, and this is the value counts. Yeah, you just value counts. So these are three, good, bad. So these are the two quantities that we have. So we have a binary classification here. But if you want to proceed to the labeling, just let's label it manually instead of using any encoders, label encoders previously, because we had lots of them there. Yeah. Here, let's label it manually. Data quality will be 𝗤2, and the quality will be labeled as bad and good. Yeah, so we have bad and we have good. So good will be 1. Oh, this is bad, and this is good. This is called manual labeling. So we manually labeled. We said, okay, map it. If it's bad, put it 0. If it's good, put 1. See, this is called manual labeling. And just run it. What it says, I really don't know. Okay, that's okay. Thank you very much. Next time we will not be doing that. Says that don't use this map method. So this is now, see, the quality is not now good 1. Everything is now numeric. See, this is how you have to do. Next time, what we have to do, we have to split the features, yeah, and the target variable. So how to define the features and target variables. Features called X, large X, capital X. It will be the data2 dot drop columns quality. You know what I have done here? I said just drop quality all these others are the features. Instead of writing all of them separately, I just drop the quality. I said drop the quality and all others are features. And the quality is the target. Very simple thing. So this, you have split the data. When you have split the data, now you have to normalize the data. So why is normalize? Because whenever you're doing some models, so normalization and scaling is important. I'll be not going to that details of scaling and all those things because I think you already know that. But scalar, let's say, okay, we should have standard scalar, yeah. So standard scalar. This is a function from scikit-learn, yeah. So that will be the scalar. And now x data scaled will be actually the scalar dot fit transform this x. So just scale the x data. Run this. I hope it will work, but it will not work because standard scalar is not defined. Very good. From the Python platform, from the Python scikit-learn, we have to bring the standard scalar. So this was the standard scalars that we have brought here from scikit-learn, if you remember. That is very good. Now standard scalar is there, and we have standard scalar, and we scan. Now we have train test split data. So this is how we can define X train and X test. So how to do that? X train, X test, Y train, Y test. All of them are equal to. All of them are equal to train test split. Train test split of what? Of X scaled, Y, and test size. You have to define the test size here. Okay, test size, we defined 0.3. You can 0.2. We can define it. We can do it 0.3 as well. So then you just define that, the splitting the data, and after that we have to check the data set readiness. So how to check the data set readiness? You have to understand the xtrain dot shape of the data set and xtest dot shape of the data set, and after that, y train shape, y test shape, y train dot shape, y test dot shape, and then missing values. So these things that you have to understand from the data set. And when you have done this, your data set is ready, then we will be starting developing a model for this data set. So now you understand that we have only two functions here, two classifications. Which model we will be using? Logistic regression model, the simple one. Then we will be using the logistic regression model for this function. This is a binary question, 0 or 1. So based on these features, we will decide the quality of the apple. So I think the time is finished, and we are 10 minutes overdue, and I understand that lots of things that lots of students will be leaving. However, I think I will be continuing this model for you and record my video and then share with you the result of what happened. Today is our last session. We will not be having such a session that everyone will be participating. We will be dividing you by groups, and each group will have its own tasks and its own model to develop, model to predict, and their own profiles. So we will be dealing with you then separately, and then after the grouping that we just divide you to groups, then we will be having separate WhatsApp groups with me, each team, and we will be having different times of meeting, I think. So then within those specific groups, we will be deciding which time will be suitable that we have to meet. Otherwise, we can discuss the results there as well, and the separate teams. So this is our final last general session. And I think I provided lots of lectures, hours and hours. I don't know how much it was impactful for you. You didn't also provide any feedbacks, as Dr. 𝗗𝘃𝘃𝗃 in the group, but I hope you will be providing that. So later on, we will be discussing in groups, because we cannot have with a large public one task or one project or one thing. So you will be having different projects, different solutions, everyone tailored to their specific needs and requirements, whatever is there. So thank you for attendance, and thank you for the participation in this series of courses that we had. After the private sessions, group sessions, that it will, I hope it will last for 2 or 3 weeks, and you will be ready for the certification. Then after that, we will be having a final completion ceremony. Maybe everyone will be participating. But this is how we concluded our last module from the curriculum that we have decided at the beginning, starting from foundation, ending to machine learning. And I hope all the basics you have, and have it there. Any comments, questions, please ask me. Okay, no questions. Thank you. Thank you for the participation. Have a good night in Kabul, and have a good time in any other place in the world. شما رو به الله تعالی میسپارم. سوال نیست. شما رو شب خوش